In this video, we're going to look at some substitutions for integrands involving a rational expression of sine x and cosine x. Now, these substitutions will work best when you don't have a function in the numerator, only in the denominator. So first we'll look at how these substitutions are derived, and then we'll look at some applications, how to use them. We'll look at one example in this video and then a few more in subsequent videos. So here's my substitution. Got the half angle for tangent. Tangent of x over 2 is equal to sine of x over 1 plus cosine of x. Now that's just a trig identity. There's two forms of it, and this is just one of them, and that's going to equal to your u. Now in the second one here, all I did is we took the u and squared it, so it'd be u squared, then it's sine squared, 1 plus cosine of x squared, and then we replaced the sine squared of x, again using the Pythagorean identity, by 1 minus cosine squared of x. Then this factors out, difference of squares, 1 minus cosine of x, and 1 plus cosine of x, and the 1 plus cosine of x divides this one, leaving me with 1 plus cosine of x. And then we need a representation for cosine and sine, because those are the functions we're talking about for these substitutions. So to get cosine of x equal to what I have right there, all we did was took the equation 1 minus cosine of x over 1 plus cosine of x equal to u squared, and we solved for cosine. So in other words, multiplying both sides by 1 plus cosine of x, we get u squared plus u squared cosine of x. So this equals to u squared, multiply both sides by 1 plus cosine of x. We get this on the left side, and on the right side we're left with 1 minus cosine of x. And then we solve for cosine. So let's get the cosines on one side. So we get u squared cosine of x is equal to 1 stays over here. We bring the u squared over, or I should say leave the u squared here. So the cosine comes over from the right side. Get a plus here. U squared goes over. So this is minus 1 minus u squared. Factor out a cosine here on the left side. We're left with 1 plus u squared. And then we simply divide now by 1 plus u squared here, both sides. So I get cosine of x is equal to 1 minus u squared over 1 plus u squared. So that means when you get a problem involving sine and cosine, the substitution for cosine of x is going to be 1 minus u squared over 1 plus u squared. So that's how this was derived. Now for the sine of x, this one, we're using this part right here, and we're just going to multiply both sides by 1 plus cosine. So on the right side, I'm going to be left with sine of x, and then the u is multiplied by 1 plus cosine. So this is 1 plus. But remember, we're looking for sine in terms of u, and we already have cosine here. So instead of putting a cosine here, we'll put what cosine of x is equal to. So it's 1 minus u squared over 1 plus u squared. And I got the u here, and let's make the 1 plus u squared over 1 plus u squared. And you got the plus 1 minus u squared over 1 plus u squared. And this is sine of x. So now let's combine what I have here in the parentheses. We got a u squared, denominator is the same. And this is 1 plus u squared, because you can't make it out here in the denominator. And then on top we got u squared minus u squared cancels. We have 2 left over in the u, so this will be 2u over 1 plus u squared. And that's equal to sine of x. So that's how these are derived. Cosine of x is 1 minus u squared over 1 plus u squared. Sine of x is 2u over 1 plus u squared, where u is this quantity. Now, there's also one where you use this. So for this substitution, Those are the main formulas. And then, of course, we need also the dx, this one. So we're going to use this right here. U is equal to tangent of x over 2. So what I did here, we took tangent inverse of both sides, or arctangent of u, and then arctangent of tangent of x over 2, of course, gives me x over 2. And then we take the derivative of x over 2, what is dx, and the derivative of arctangent is du over 1 plus the square of whatever u is. And then, of course, the 2 comes from this right here. So whenever you have these types of problems involving a rational expression involving sine and cosine, the dx will be replaced by 2 du over 1 plus u squared. And, of course, the cosine and the sine are replaced by those. Now, there's also another one. It's going to look very similar to what I have here, a little bit different here though. And this is called the Weierstrass substitution. I think it's German maybe. So notice here, the t, we don't use the u here. It's t is equal to tangent of x over 2. And of course tangent of x over 2 is equal to t, that's t over 1. So here's the angle, got a right triangle here. Tangent is opposite over adjacent, so that's your t over 1. Complete the triangle, and then this is a right triangle. Hypotenuse is equal to the square root of 1 plus t squared. So notice then, the cosine of x over 2 from the triangle is adjacent 1 over hypotenuse, 1 over the square root of 1 plus t squared. The sine of x over 2 is opposite over hypotenuse. So it's t over the square root of 1 plus t squared. Now those are the substitutions there. But remember, this is going to be for problems involving sine and cosine of x, not x over 2. So we have to rewrite it. So here's the way this is done. Have this here, and then the sine of x is equal to, I'm going to use some identities here. So it'll be sine instead of x, I'm going to put 2 times x over 2. That's the same thing as double the angle. So I can rewrite that as 2 sine of x. Again, I'm using the identity for sine of twice the angle, which is 2 sine times cosine of half this angle. So if I just put an x there, it comes out to this. And I'm doing this to get the representation for sine of x using this substitution. Okay, so we're talking about 2 substitutions here. So from here, I have 2 sine x over 2 cosine x over 2. So look at the triangle here. Got the 2 there, and then the sine of x over 2, opposite over the hypotenuse, times the cosine, okay, that's the adjacent over the hypotenuse. Multiply this out, square root of 1 plus t squared times the square root of 1 plus t squared, that gives me 1 plus t squared. And then 2 times t times 1 gives me 2t. So if you're doing the substitution for t equal tangent of x over 2, well, you have the sine, you're going to replace it by 2t over 1 plus t squared. Now to get the representation for cosine of x, I do it this way. Cosine of x is equal to, because I have x over 2, I have the cosine of x over 2, but I want the cosine of x for those types of problems using this identity right here. So this will be 2, and that's going to be the square of cosine of x over 2. So cosine is 1 over square root 1 plus t squared, and that is minus 1. So we're going to square this, so this will be 2 over, and square the radical, I'm left with 1 plus t squared. That's minus, need the same denominator, so I put 1 plus t squared here, and 1 plus t squared up here. I go 2, same denominator, so we can combine. 2 minus 1 is 1, and then we have the minus t squared So we get that. Now here's the situation. If you're given a problem involving an integral that has an integrand with a linear combination of sine cosine. So that's what you want for these types of problems. You want in the denominator, you simply want a linear combination. So you don't want sine squared or cosine squared. If it has sine, 2 sine of x minus 3 cosine of x, that's what this is for. Now, if the instructions don't tell you to use this kind of substitution, then I would just solve it the usual way. Just the standard U substitution work. If it does, go ahead and use it. Or maybe using a trig identity will simplify the integral to something that's easier to evaluate. But before we go to an example, just wanted to point out again that if you have a problem where you have multiples of sine and cosine in the denominator, some other methods don't work. You can't use partial fractions. Integration by parts doesn't work. Standard U substitution doesn't work. And they don't specify, then you can use these formulas. So if you're going to use this method here, where your main substitution is going to be sine x over 1 plus cosine of x, then the cosine, where we have a cosine, you replace it by 1 minus u squared, 1 plus u squared. Wherever you have a sine, replace it by 2u over 1 plus u squared. And then the dx is replaced by 2 du over 1 plus u squared. Now, if you're using the Weierstrass substitution, this is what you're going to use. The t will equal to tangent of x over 2. The dx will be 2 over 1 plus t squared dt. And of course, your sine and cosine are over here. So, for example, if you have the integral of, say, 1 over 1 minus sine of x dx. If you're given this problem, the integral of 1 over 1 minus sine of x dx, and they don't specify how to evaluate, then you can use any of the methods that you used before. This one right here, I would multiply by the conjugate. If I don't have to use those substitutions I just went over, I would multiply the numerator and the denominator by the conjugate of what I have in the denominator. So then this is transformed to an integral that has a 1 plus sine of x in the numerator, 1 plus sine of x, and then this product in the denominator is 1 minus sine squared. Then I would just divide the 1 plus sine of x by each term by cosine squared x. And I actually did this integral in one of the videos that I did a few weeks or maybe months ago. That's going to work fairly straightforward. Just a couple of minutes to solve it. If they say to use, say, the first substitution. So for that one then, the sine of x is replaced by 2u over 1 plus u squared. Got a 1 here. And then the dx for that one is replaced by 2 du over 1 plus u squared. Then this is equal to, now the denominator, notice I got a 1 plus u squared, a 1 plus u squared, so I'm going to just multiply through here. So 1 plus u squared times 1 is 1 plus u squared. And then the 1 plus u squared here cancels that one. That gives me a minus 2u. Numerator, I simply have a 2 du. So notice, this simplifies nicely here. Got the 2 du in the numerator. And then I've got the u squared. Maybe rearrange these, and then it's a minus 2u plus 1. And that's one of the reasons I use this substitution. It looks like it's going to be kind of messy, but because of this 1 plus u squared appearing in most of these substitutions here, you wind up with a rational expression. Notice, and 2 du, and then u squared minus 2u plus 1. Plus 1, that's the same, that's a perfect square. So it's u minus 1. That's quantity squared. And if we take that to the numerator now, this will be 2 u minus 1 to the negative 2. And because the derivative of u minus 1 is a 1 with respect to u, this is the same thing as integrating say u to the negative 2, or something like x to the negative 2 with respect to 2x. Here I just had 1 to the exponent and divide. This would be a negative 2 here, and then this would be a u minus 1 to the negative 1 plus the constant of integration. Now I'm going to put this up here now, go up here. And now all I have to do is go back to the substitution. So this is going to be minus 2 over, I'm going to take this to the denominator. That'd be u minus 1. But what was u? For the first substitution, u was sine of x over 1 plus cosine of x. Then it was minus 1. So now we just simplify this out a little bit here. Minus 2. Get the same denominator here. So this would be 1 plus cosine of x. And then multiply this numerator and denominator by 1 plus cosine to get the same denominator here. So this will come out to sine of x minus cosine of x minus 1. So I just find the common denominator here. 1 plus cosine of x. I get this. And then we got a complex fraction here. Let's just multiply by the reciprocal of this. That would give me then a minus 2. Put it in parentheses here. 1 plus cosine of x over sine of x minus cosine of x minus 1. And of course we have the constant of integration. So that's the final answer for this one. You get a minus 2 times the 1 plus cosine of x over sine of x in the denominator minus cosine of x minus 1. Now, if you were to work out this problem without using this substitution and doing it the way I told you, or the way I demonstrated, where you multiply by the conjugate, the answer is going to be different because of the procedure, but they'll both be correct. Different form, but you've seen problems like that where you work it one way, you get one answer, work it another way, you get another answer. But if you check it, it's going to work. Or if you use some trig identities, you can rewrite it one in terms of the other. This is the answer. We'll look at some more examples using the other substitution, the t substitution. That'll be it for this integral, for this video. Thanks for watching. We'll see you next time.